All right, guys. Thank you so much for hanging around. This is the last hour for for today's uh, workshop. So what we're going to do today is we'll look at some more machine learning models, a little bit more involved than what we have been looking thus far. We'll talk about decision tree, random forest, and XGBoost. Given, I think, like another time, I would be able to cover a decision tree and random forest, but I've already provided notes for XGBoost. So those of you who are interested can look through the notes, and if you have any questions, you can email me or ask in the chat. Uh, Briefly, I'm faculty member in School of Chemical Engineering at Oklahoma State University. And then I'm one of the co-PIs of this workshop grant that we have from NSF. All right. So in terms of topics, we'll be discussing decision tree models, and then how we can improve on a single decision tree through the procedure known as bagging, which is nothing but bootstrap plus aggregating, which leads to what are known as random forest models. We'll do some hands-on exercise. And then gradient boosting and extreme gradient boosting, also known as XGBoost. We have notes available on the GitHub repository. All right, so let's get started. So when we think about decision tree models, what we are really talking about is a supervised learning model. So we learned that there are three different types of learnings that we can do: supervised, unsupervised, and reinforcement learning. In terms of what decision tree is, it's a supervised learning method. So you have inputs and outputs. It can be used both for regression and classification problems. So there's really good thing about decision tree models that we have, that they are applicable, and it's a non-linear model. Thus far, at least for linear regression, we were talking about linear models, but decision tree models can capture non-linear dependence in the data. And it is very, a single decision tree is easy to understand because it will be in the form of if then else statement. And then I'll show you in the next slide what do I really mean by if then and else. It's a non-parametric model, so we don't really need to fit any parameters, but there are hyperparameters that will tune to get as good of a performance as possible given the model that we are choosing. And it's a piecewise continuous. Once again, when we do a model development, I'll show you what we really mean. And in fact, when we look at this particular data set, it's just a schematic representation. We have two features, X1 and X2, and then we have certain data points that are given. It could be a regression. Let's say it's a classification problem. So you might want to partition the data in such a way that if X1 is less than this particular value T1, then the data will be partitioned into two categories. So here you have yellow dots, and then on the right hand side you have blue. And then you might say, okay, I want to do more partitioning of the data. So you might actually say, okay, if X2 is less than S1, then I'm in this particular category, while X2 greater than S1, you will be in this quadrant, if you will. So if you think about what are the conditions that need to be satisfied. So for this particular region, I need to have X1 greater than T1 and X2 greater than S1. And then we can go through each of these regions to figure out what conditions might apply. So as I was saying, if then else, right? So if X1 is less than T1, then we have this particular data set. If X1 is greater than T1 but less than S1, then we are in this region. So you will have this cascade of if then else statements that actually builds your tree. So there are some terminologies that we can learn from this slide. So the very top decision that you make is called root node. So In the previous example, I showed you that, okay, if x1 is less than t1, then, that's when we'll start. So, that condition can be, true, or it can be false. So now, depending on whether this condition is true or false, you will have these two branches. So now you have these two regions that you are separated, and each of these will be called a branch. This branch will be corresponding to the condition being true, and this will be followed when this condition doesn't satisfy. And then, as you can imagine, that you can have multiple of such decisions to make. So next would be, oh, if x2 is less than s1, it is somewhere intermediate. I mean, I've not fully drawn the tree, but this is not the end of the tree that we are building. So it will be called an intermediate node. And then you can keep going this further and further, so that you can start building this tree. So you start with the root node, you have a bunch of intermediate nodes, and at the very end you will have what is known as a leaf node. So once you hit the leaf node, there won't be any more splitting, particularly in that branch. And then, going from root node all the way to the leaf node, will call this depth of the tree. So maximum number of branches to reach a leaf. So that will be called, how deep the tree is. So as you can imagine that, I have to make a bunch of these decisions that, what is the depth of the tree? How many samples would I have in each of the leaves and things like that. And as you recall from ridge regression, that we covered, these are not the parameters that are set or determined by the model that we develop. We have to kind of set these parameters, and there'll be hyperparameters, and we'll see how to set these hyperparameters, and figure out what's the optimum value of these hyperparameters might be, given the problem that you are solving. And this is called decision tree. In a way, it's kind of inverted, that you start at the root node, and then you have branches, and then it ends in leaves. So that's why it's a tree. You are making decisions at every node, whether to go on one branch, which is true, or on the other branch, right? So you can build this decision trees. And as you can see, there's a very simple, um, uh, it's very interpretable, it's simple, and it's easy to kind of figure out what decisions are being made. All right. So now, if you look at this particular tree construction, we have to make a bunch of decisions, where to split, what values to use, and things like that. So, like what we did in regression, we have to have an objective function. So the objective function that we'll use will be to minimize this residual sum of squares. So what is the residual sum of squares? So if I have a data point yi, then we will figure out what is the difference of the average response that one would have in that particular region. And then if we sum over all the regions, I want to minimize this residual sum of squares. This might be a little bit opaque at this moment, but we'll make it a little bit easier in the subsequent slides. So here, J represents the number of regions or the feature space one partitions into. So if you go up, when we uh, have this root node, I'm partitioning the entire region into two regions, one corresponding to x1 less than t1, and one corresponding to x1 greater than t1, and so on. So, and depending on that condition, some points will be in region 1 versus region 2. And the response of each of these regions is nothing but the average response that we have. All right, so let's make it a little bit, more intuitive. So typically, this what happens. So let's take this example that you have a feature X, And then there's the cutoff value S, which divides the region in two parts, R1 and R2. And you have, in R1, three data points, Y1, Y3, and Y4, and in R2, Y2 and Y5. So, how we'll look at our objective function. So our job is to minimize this residual sum of squares. So we partition this residual sum of squares into two sums, one that belongs to region R1 and the other one in which the data points are in R2, right? So when we look at yi in region 1, we will have I equal to 1, 3, and 4. And what would be the average response? It'll be the average response would be the average of the three data points, y1 plus y3 plus y4 divided by 3. So it's a simple arithmetic average. And similarly, we can look at y2 or region 2, where I have y2 and y5 that are present. So the sum will go over y2 and y5. And then once again, the average response would be nothing but the average of y2 and y5. So now, you can imagine that, I can go through this S and I can change the value of S, which will, mean that maybe some of the points are now in, let's say, for a particular value of S, you only have y1 in region 1 and the rest are in region 2. So for every S value, you will compute this residual sum of squares, and the value that minimizes the residual sum of squares would be the one that the tree will partition into. Okay. So this is how, you can do a recursive partitioning and things like that. So it might so happen that, as you go down the tree, the initial decision that you made may actually result into better split, but that's not what we do. So it's called top down greedy approach, and it's called recursive binary splitting. So when you begin at the top, you are only going to look at the partitioning that you make at that particular juncture. So you wouldn't worry that, if I went down maybe five branches down, then I can improve the splitting at the root node. No. So at every time, at every branch, you're just going to look at what is happening locally. So it's kind of local algorithm. All right. So this is what we do. But when we do something like this, there are disadvantages, or advantages and disadvantages. So advantages, it's very easy to interpret because you can quickly go through the tree uh, for simple data set and simple model. If you don't have a large number of features, uh, that it's ease of interpretation. So you can figure out why you are getting particular value that you are getting. You can graphically look at this, and then it's good understanding by a non-expert. So you can explain to people who are not doing machine learning, and the scaling of features is not required. I mean, it's not such a big issue, but let's say you forget to scale your features. So in the previous example of perovskites, we saw that when you scale the features, the performance of the model changed. Here, the scaling of feature is not required because at every point you are just looking at the same magnitude. So your y is the output has the same units, right? So even if your uh, e- even if your features may have widely varying units, it doesn't really impact your output features. However, there are disadvantages. These decision trees can be prone to the data that you select, and it can be prone to um, overfitting. So if you change your input data to train the model, then your trees can change drastically, right? So as outputs are only piecewise continuous, sometimes what can happen that multiple inputs can yield identical results. And then we'll actually see this in Google Colab when we do some of the exercises. All right. Before we go on to the next section, we'll actually do hands-on exercise on Google Colab just to get the feel of how you might go about developing a decision tree model, and then I'll also take questions if there are any. Okay. All right. So let me stop this and then share. All right. So if you click on this link, it'll take you to once again this workshop. So like we'll click on Monday, copy the link, and then we will go to Google Colab. All right. So we'll do GitHub, and then we'll paste this link. It takes some time.
I think you need to hit enter, Dr. Shah.
Yeah, I mean, I'm hitting enter, but
okay, then you need to add the file name. There's the file name.
say it again.
I think you need to add the file name here. RandomForest.ipython notebook file.
Yeah, I think like it's now loading. So okay. So if you it may take some time for you, but then you should be able to see this to Python notebook. And since you probably already did, you have it, right? Okay. So is everyone at this point?
Yes.
Okay. Great. So what we'll do is we will clone the entire repository of Git repository, and then as more and more information is added, a directory is added, you will have access to that. So let's do that. Okay. So it runs without any issues, and then what you can see, like if you click on this file folder icon, you should be able to see ninth workshop ML for molecules. And if you go to Monday subfolder, you have like everything that's available to you. So there's also decision tree random forest PDF that I've uploaded. This IPython notebook data set and things like that. Okay. All right. So we have already gone to this directory. We've changed the directory. Let's import some of these packages, NumPy and Pandas. And then we are going to load this particular data set. So this data set, so let's first look at the data set. We have DF featureized head. So, this is, a little bit of my research area where we are looking at what are known as deep eutectic solvents. HBA stands for hydrogen bonding acceptor, hydrogen bond donor. There's experimental data that we'll use to develop a model, and the experimental data is for surface tension. And then, it has some data are for training, some for testing. So we'll actually get there. What is the ratio of HBA to HBD? So you can change these ratios to figure out. And then here, this is where you'll start probably doing molecular level machine learning, where converting chemical structures into what are known as smiles, and then extracting features. So here, HBA all the way to the end, there are different features, which these are called 2D descriptors that you get from RDKit library. And more about this you'll learn, I think, probably tomorrow. But this is what the data you have. So let's hide the output, and then let me add some more information. So let's actually look at the experimental data. So for DF featureized, and then if you look at the experimental data, and let's plot. So we'll plot histogram. There's something that you just saw for balance and balance, or like the validation and train data set and things like that. Okay, so here we are looking at surface tension data, which goes from as low as close to 30 dynes per centimeter, all the way to 72, probably like this for water. Or like some of the deputatic solvents that are that have high surface tension. So as you can see, there's reasonable uniformity, at least for 30 to 50 dynes per centimeter. And then there's some data which is not very well represented, but this we will ignore this kind of discrepancy for now. But if you want to be a little bit careful, then you might actually balance the data out and things like that. All right. So this will shuffle the data. It's not really necessary, but we can do it. And then we just looked at the top features. Let's also look at what the overall data looks like. So we have total of 771 data points, mean of the surface tension experimental data, 45 plus or minus 9, minimum is 31, all the way to 75. I just showed you the histogram plots and things like that. And here are different values of your descriptors. Once again, if you were doing this research quality publication, we would make sure that there is enough variability in each of these descriptors and things like that. But there's more for demonstration purposes. So I just wanted to show you how you can look at the data. And there's something that I always encourage. Professor Biladu also recommended that you always want to look at the data, just not treat them as a black box. We'll do splitting. So let me actually show you something before we do splitting. Let me so if I do DF featureized, and is what are the columns that we have? Okay. Let's just do DF featureized. Let's look at the columns. Yeah, so here you can look at all the columns that we have. And then when you look at the status column, that will give you whether it's a training data set or test data set. Typically, like, what we do, you might remember from the linear regression part that, you use test and train split method to split your data. But here, we already have data set that actually has data labeled as test and train. So like, you have training data set, and some of them are testing data set, and so on and so forth. Okay. So all we are doing is that, like, whenever status is training, we are, extracting the experimental data, we are putting in Y-train, and X-train is, we are dropping some of the things that are not really features. So like, smiles is not a feature, status is not a feature, and so on and so forth. So, and the same thing we can do Y test and X test. Okay. So it's split, and then now we have train size 615, test size about 150. So we have, 4:1 ratio. About 80% of the data is training data set. 20% is test data set, which is like, typically a good split for most of the balanced data set. Now, here is the main crux of what's there in terms of decision tree. sklearn, once again, is a very powerful library for a lot of these machine learning models that we are learning today. So sklearn, there is this a model called tree that we're going to import. And then, if you want to look at plotting and stuff like that, we can do that as well. So hopefully, like, you are kind of getting the pipeline of how these models are developed. You import the data, then call the model that you want to use, and then instantiate the model. So, in linear regression, we had, say model equal to linear regression, and whatever parameters that we wanted to supply. For example, if you wanted to set the intercept to be 0, you could do that. Here we are saying, okay, maximum depth equal to 3. So if you remember from the presentation, we had like, how deep you want to go. Here I've said like the maximum depth equal to 3. Once again, like, just for demonstration purpose, but this should kind of like a trigger, or maybe this is a hyperparameter. Why not 5? Why not 1? Why 3? So, there's something that we need to kind of optimize hyperparameter, right? And then once you define your model with, optional parameters, you supply training data set, input and output. So let's do that. And then we do prediction. So every machine learning model will have like this method dot predict, where you supply the training data set. It'll give you the corresponding Y predictions, things like that, right? So here it says, training mean squared error is 16.56. So, once again, this is in surface tension. So, there's a little bit of error here. So same thing is for Y. Now, like, as I said, the beauty of decision tree models is that we can actually plot. So, but before we do that, what I want to show is, let's actually print. What do I want to do? Yeah, so let's plot Y. We'll plot Y train. So we just want to look at Y train, and then the prediction that we got, Y predict train. Okay. So maybe let me do scatter. Okay. So as you can see, this is your Y train and what you're predicting. So your Y-axis is a prediction, and then just so that we have the y equal to x line, the parity plot. So let's plot y train, right? So as you can see, this is actually what your model should have captured. This is the data that or the line that it should have captured. But we see that these are these horizontal lines. So as I said, the model will predict for some inputs the same value, and that's why you get these horizontal lines. Um, so your model, it's a piecewise continuous model, and you can improve upon by choosing maximum depth and things like that. And once again, if you changed your trained data set, this would change drastically. So that is something that you want to be mindful about. We never use decision tree model by itself, but it's a good start for random to learn about random forest model. All right. So here is what you can do, that you can actually plot the model that you just developed. So I'll probably zoom in a little. So it says, okay, whenever this particular feature was less than or equal to this value, if it is true, go down this branch. If it is false, follow this. And then as you can see, it is looking at various now splits. So there's the root node, you have intermediate nodes, and then more intermediate nodes before it ends. And we said maximum depth equal to 3. So if I start from the root node and then reach the leaf, I have 3 branches, 1, 2, and 3. So I need to go down 3 branches to reach the root level. So and as you can see that every time it splits, your squared error is actually going down. Here you have 87, there's 68, 47, and so on and so forth. And then it also tells you how many samples you have. So you started with 615 samples. In this bucket, you have 114, 501, and so on and so forth. Now, this is where you were seeing all this horizontal values. So if you are in this bucket, what it says that for 53 samples, it's going to predict 55.9 value. So it doesn't matter, these could be very different, but there are 53 samples or 53 data points for which it's going to predict 55.93. So if we go back here, you can probably see maybe these are the data points that it predicts the same value. A little bit less than 50, there are a large number of data points. So let's look at where this is. Right? So yeah, 47.27, 300 samples, right? So this is not a very good model, but now you begin to appreciate that, if I just do decision tree model, it's not going to be, very robust. We can, keep increasing the number of trees. So instead of 3, let's say if I want to do 10, what happens? Okay, so now my train MSE, goes down quite a bit. Test MSE also goes down, which you expect. And now, this model is becoming closer and closer to y equal to x line, especially it started doing well in the low surface tension region, right? So, but it's a very deep tree, so you have to make a lot of decisions before you get there. Even here, there are points that are about same value. So how do you improve upon those results? Okay. All right. So we talked about decision tree models, and then we did this Google Colab. I'll pause maybe for a couple of minutes, see if there are any questions, if people have comments. Okay. All right. If there are questions, feel free to put them in the chat, and we'll get to those. Okay, so now let's move forward and then discuss how we can improve upon decision tree models. So there's this technique called bagging, which is bootstrap and aggregating, which leads to a random forest machine learning model. All right, so let's actually understand what a bootstrap sampling is. So let's say we have like 5 data points, but this is your original data set. And now, I've just labeled, I've just shown different color to show that there's different data point. But what you want to do is you want to randomly draw samples with replacement, right? So if we randomly draw samples from this, maybe initially you get red, you put red back, and then you get red again. You might get yellow and so on and so forth, right? So this is your bootstrap sample. So now if you look at the original data set, you have this bootstrap, you have a little bit of repetition, but now that's the original data you have. You can't go out and measure more data points or measure perovskite stability. You cannot just go and say, I want 100 more data points to improve the model. Right? And we can keep generating these bootstrap samples, and then what we can do in the end is for each bootstrap sample, we develop a decision tree model and predict a response FIX. So for every bootstrap sample, we generate a decision tree model, and then let's say you make a prediction for a given data point. And then in the end, what you're going to do is if you generated B number of decision tree models, 100, 200, then you're going to average your response. So, random forest or this particular process is nothing but generating, large number of trees and then averaging response. So as you can imagine, when you generate one decision tree versus 100, your computational time is going to increase. All right. So what's the random forest model? It's a multiple decision tree based model. It is carried out on bootstrap data. You may not have the original data set that you are developing on this. So now, you're putting a lot of randomness so that your model doesn't overfit, right? So that is something that we always try to do, that models are not overfit to a particular set of training data set. Otherwise, your predictions become sometimes challenging. And then it achieves decorrelation of trees. One tree is independently constructed from the other because it's not seeing the same data set. And there are things that you can do. You are not using all the features and so on and so forth. So what are some of the hyperparameters that we have? Number of trees that you generate. You could be 100, it could be 200, things like that. You also select number of features to select at every split. So previously, when we built a decision tree model, we were looking at all the features to split at a node. But here, you might select only part of the features. So once again, you are building a little bit of randomness into how you are building this tree. Minimum number of samples required at an internal node. So it'll split that node only if you have so many samples. And then how many samples you should end in a leaf node. You might say, okay, I want only one sample in each leaf node so that you don't get that horizontal behavior that I was showing. But then it'll be a very deep tree. And then once again, it may be prone to overfitting. All right. So let's go back and look at the hands-on exercise that we have. We'll do the same thing on
Jindal,
the.
there are a couple of questions in the
Sure.
chat.
I actually don't see them. Okay, now I see them. Okay. Thanks. decision tree seems more suited for discrete output observable. Would it make more sense to use some sort of regression for this data, since like here seems to be continuous? Yeah, I mean, it's a good point. You can always use a little bit of or regression when you develop a model. But in regression here, like you don't have to assume a form or like an equation that you want to fit your data against, right? It's a non-parametric um, fit, so that you are not guessing whether it's linear. Do you need to have polynomial fit, things like that? Yes, it's a it's a discrete model, and that's why like we are going to do random forest where this discreteness will kind of get distributed over different trees, and then you won't have this behavior that I was showing. Yeah, but you can definitely do some sort of regression, and that's always an open question. Which model to use, right? Whether you should use linear regression, decision tree model, or artificial neural network, right? And then hopefully, like at some point we'll talk about bias and variance that can actually help you to figure out which model you might want to use. My philosophy is use the model that is as simple as it is, but no simpler, right? And always you would want to go towards interpretability rather than like yeah, you just get an output and it's hard to figure out why you got the output that you got. What is the concept of hyperparameter? What is the correct way to think about it? Yeah, great question. What's first of all hyperparameter? So in the previous presentation, or linear regression, logistic regression, or I think in linear regression, right? So we were talking about ridge regression, and then there was this parameter lambda that was introduced. Now that lambda parameter has nothing to do with the coefficients that you are fitting. So if you have a linear regression model with some ridge regression, lambda is kind of like set by the person who is fitting the model. So you can have a very low value of lambda, let's say 0.1, or very high value of lambda 100. Now, which hyperparameter or like which model would you choose? Because there are as many models as there are lambda parameters that one can think of. And in theory, you have infinite models, right? Because lambda is continuous variable; it goes from 0 to infinity. So there's this concept of cross validation, which we have not introduced yet. The ultimate goal of any machine learning model is to make predictions, right? And you want to make predictions in a way, or you want to make good predictions. So there's a concept called cross validation. So what you do is you split your training data set into number of folds. Let's say like you have 100 data points. You say, okay, like I want to split the data in 10 folds. You're going to develop a model based on 9 of those folds, like a 90 data points, and make a prediction on 10 for a given hyperparameter. And then you'll keep repeating by sort of like changing each of the folds. And I know it's kind of hard to understand. Let me see if I can pull a presentation that I may have. Okay, yes, let me. All right. So this is the concept of cross validation, and this is what you use to predict, like, figure out um, your hyperparameter. So you have a training data set, test data set. You don't touch your test data set, and you split your training data set in number of these folds. What you do is in the beginning, you develop a model based on only this data point and make prediction here. So what you are now trying to figure out is, like, for a given hyperparameter, what is the predictive capability of the model that you are developing. And then you will do this for every lambda parameter that you choose, and then pick the one which gives you kind of like highest predictive capability, so highest prediction. So by doing that, you are kind of saying that if I use this particular parameter, hyperparameter, then I'm more likely to get good predictions in a way. Okay. All right. Any other questions? Yeah. So, like, Ali Reza gave a good explanation that, oh, like, if you have this parameter, um, it's a kind of free parameter that you can tune to get good prediction. Okay. All right. Let's if there are no more questions, we can go through the Google Colab, and I think I lost it. Over here. Okay. All right. So we completed this part. So for random forest, once again, we are going to now it's an ensemble technique. So now we are going to collect a lot of these individual models and then develop a model. So here is something that we said, like a maximum depth equal to 5. So if you think about, like, what we did in the decision tree model, we had maximum depth equal to 3, number of estimators. So how many trees that I want to build to be able to make this prediction. So we are doing 200. And then at every node, I want to have minimum 3 samples. If there are no more than 3 samples, then I won't split. And then we'll have minimum sample leaf equal to 1. So it ends with 1 at the very end. So this defines the hyperparameters of the model. And then we can run this pretty standard, and we can figure out. So as you can see, our train mean squared error, test mean squared error, it's already 5.49, right? So if you remember, with maximum depth of 3, we were able, like, we were at 16 or 15 for training MSE and test MSE. So you get tremendous improvement by doing this ensemble technique. Once again, are these the best parameters? We don't know. So we are definitely not going to try to visualize, because there are 200 of these trees. Even if you, like, you could probably visualize one by one, but it won't really give you a lot of insight. So we won't do hacking, but I would encourage you to look at some of these parameters that you have for random forest options in the model. So and then play around with that. Now here is where, like, we want to figure out what is the hyperparameter search. What's kind of combination of all these parameters that I set, options that I set here, which one would give me, like, best prediction. So one can think about doing this manually. So, oh, let me try this set. But imagine you have for each of these, let's say there are, like, 4 4 values, right? So maximum depth, you can go from 5, 6, 7, 8, estimators, things like that. And there are 4 variables. So now if you think about like, all the options, you are looking at 4 to the power 4 sort of models that, you kind of go over. You can do this by writing, for loop or do loops. But scikit-learn provides a very convenient way of doing this. We already imported scikit-learn, so we don't need to do that. This is known as like, grid search CV. So all the work of like, combining various combinations, it's done by this grid search CV. So now, as you can see, there are 1, 2, 3, 4, 5 of these parameters that we are looping over. You have 2, 3, 3 here, 3 here, 3 here. So like, number of models that it develops is just multiplication of all these parameters that you have. So 2 times 3, 6 times 3, 18, 54. So close to 180 models that you are developing. But then once you define this grid, RandomForest regressor and the grid search CV will take care of it. So here is what we said. I was showing you cross validation, and I was talking about number of folds. So this is where it says, do this for 5 folds. Typically you do it for 5 or 10. But as you can imagine, the more the number of folds that you have, greater will be the computational cost. Once again, we are, working with very sort of small data sets, very toy data sets. But if you have like, millions of data points, this could get really expensive, right? So, all right. So I'll go over this. We'll take some time. Yeah, so it started fitting. And as you can imagine, like, it's going through all the folds, different combinations, maximum depth of 5. And we had like, 5 and 10 as a set. So it'll go over 5 first and then do 10. Now the maximum features change to square root. So yeah, now it's log 2. The maximum depth is still 5. Now it's increased to 10. It'll go to 1. The maximum features 1, square root, and log 2. All these things will change. So as you can see, like, it's developed large number of models. Yeah, so looks like it's finished. And then, yeah, so it came out with maximum depth of 10 features, square root. So this how it is going to choose the number of features at every node, sample size, leaf one, and then it used 100 decision trees. And once again, it can be random, but there's a way to set your random state. So those of you know about random numbers, these are a pseudo random numbers. If you can set the initial seed, this reproducible. Okay. And then we can just look at what the test set is. So what happened here?
I think this like a turn partial change, and you cannot use round like that. So you need to get rid of the function.
Okay. Thanks, Masroor. There's one more round somewhere. Okay, so here we are getting now training score, test score, so 9.5, 9.4. So we are getting a pretty high scores. So there's something that we can do. So let's get rid of this round. Okay. I think I have parentheses. Okay. All right. So now we are able to get reasonably good results with random forest. There are some data points that are kind of still we are predicting same values, but yeah, overall the model has improved quite a bit. Our mean squared error has gone down to 4.5. So as you can see, you can improve these models by doing sort of ensemble technique, by bringing a lot of trees and their outputs together. Okay. Looks like there may be some comments or questions. Let's see. I used np.round network. Okay, great. Thanks. All right, so this concludes our tree-based random forest machine learning models. You have the notes where I've also given the concept of XGBoost. What I would encourage is, go through that and maybe try to develop an XGBoost model. There are a lot of things kind of we are glossing over, but if you have any questions, feel free to email us, or I'll be around for a few minutes and you can ask me questions. All right, guys. Thank you.
Thanks, Jindal. So thanks everybody for participation today. We will pick back up tomorrow. So this was just sort of like trying to get people on board with ML concepts. We're really going to start tomorrow with the molecular part of this, especially, okay, great, we know how to do machine learning with numbers, but how do you do machine learning with molecules? Those are not numbers. So how to get molecules out, numbers out of molecules and use those is really a key theme for tomorrow, and will come up throughout